In this class, we're going to consider a technique called integration by parts, and this is a technique we use to evaluate integrals which are in the form of a product. So a little bit like the product rule for differentiation. So sometimes if you've got a product, you can manipulate it in a way that puts it into a form you know how to integrate. For example, if you had, say, a bracket and another bracket, that's a product, but instead of dealing with that as a product, you could multiply the brackets and then use the power rule. But there's scenarios like these scenarios here where you don't have that option. You can't put these into a format that you know how to integrate, so we need another technique, and that technique is called integration by parts. So we're going to take a look at these examples in a moment. It's not an easy technique, this one, so give it particular attention. It's quite a common technique in integration, a common question type. But at first it is a little confusing, I would say. So do take your time and be patient with understanding this, and it's definitely one that you require a bit of experience with as well. So the general kind of layout here is something like this, where you've got a product of functions. So this would be our first function, the sine x is our second function. Here we've got an x squared function and then an ln x, so natural logarithm of x function. So in general, you're looking at this kind of scenario here, a function times a function, and you want to integrate that whole thing. So that's usually not how it's quite written, so we'll just kind of park that just to think that's the general overview of function times a function. More specifically, what we're looking at is this scenario here. Now, this looks a little ugly, so let me just explain what's going on here. This is basically the form that we're looking for to use the integration by part technique. Now, you might not natively have this form in your question, or it might not be obvious that you've got that form in the question. So sometimes you've got to manipulate the integrand, the thing you're integrating, to put it in this form, or more commonly, you've just got to choose the correct assignment of a u and a dv, and I'll explain this more when we get into the examples. Making the correct assignment of those letters then allows you to recognize that this is in that form, and you can then use the technique that we're going to explore in this class. And the technique says if you have an integral in this form, so some function u times a derivative of some function v, so you're basically assigning one of your two functions to be a derivative already, then the solution, if you like, to this, the way you would evaluate this is uv minus the integral of v du dx times, or not times, but with respect to, sorry, not times, with respect to x, so dx. So if you've got an integrand in this form here, u dv dx, and you're integrating with respect to x, then that would evaluate as uv minus the integral of v du dx dx. Clear? Probably not, right? It's a little bit of a strange looking formula. But basically it all comes down to making the correct assignment of u and v, or well, u and v, but u and dv initially. So let's just look at an example. Hopefully an example will make it a little clearer. So here we've got our product, and we need to assign u to one of these and dv. Now, there is a bit of a skill, kind of an art, and a bit of experience really in knowing which one to assign. Sometimes you can go in a bit of a loop if you make the wrong assignment. But usually it's fairly, well, it's not fairly obvious, but you'll get experience quickly to know how to do these. You don't need to work too many of them, is what I'm really trying to say, to know what to do. So let me just show you. So for this one, let's set it up as our u being equal to the x function, and then we're going to set up our dv, so this part here, the dv dx, as being the other thing, the other function, the sine x, okay? So all that I've done there is assign these two parts. This is why it's called integration by parts, I guess. Assign the two parts to the two separate functions. That's always your first step with these, making that assignment and then working it from there. So looking at the formula says we need a u and a v. Well, we've got a u, we don't have a v, so we're gonna have to create a v, and we need a du dx, which we don't have, but we can create from this here. So basically we're going to differentiate this guy here, so we're going to get du dx, which just equals 1 in this case. That's a very simple scenario. To get this to v, we've got dv dx, we're going to have to integrate this. So if we integrate like that left-hand side, if you like, with respect to x, we would get back to v. If we integrate sine x, now you might not know how to integrate sine x yet. I don't know if we've covered that yet in this series of videos. I think that's coming up later on, but you could skip ahead and check that out, or let me just show you, because the integral of sine x is just minus cos x. Just the opposite of the differentiation rule. So sine differentiates to cosine, it integrates to negative cosine. So now we've got basically all the bits that we need to plug into our formula. So that would tell us then that this guy is just equal to uv, so this is u, this is v, so that's minus x cos x minus the integral of v du dx. This is our du dx. In this case, it's very simple. It came out to be just 1. So this part here is just 1. V is minus cos x. So minus cos x in here. I can actually pull that minus back through the bracket. Instead of writing in minus cos x, sorry, not back through the bracket, back through the integral. So instead of having minus cos x, I could pull the minus to make it a minus minus, which will just make it a plus. Cos x. That will just save a line of working basically. So we get that there. That's just a direct substitution into the formula. And then we can just take this one step further by going minus x cos x, taking the integral of cos, which is positive sine, and then remembering your plus c on the end for this integral. So that there would basically be the solution, the integral of this product here. So you can see that once you've made your assignment, and actually your assignment of the u and the dv, it actually then flows quite easily from that point. The rest of it can be, usually can be quite straightforward. But the challenge is, as with a lot of differentiation and integration, a lot of calculus, the original integrand is going to vary. So this is obviously very different to this. This is different again. It's getting used to the different scenarios that can be a little challenging. So let's take a look at this one. Now, for this one, it's not always the case that you make your u equal to the first term in the product, okay? So this time I'm actually going to switch it around, and I'm going to let my u equal the ln x function. And I'm not going to really focus too much on why I'm doing that right now. We'll chat about that later on. So that would be the u, and then therefore the other term that we need, the dv dx, has to be the other term in the product, which is x squared. Okay, so we've made our assignment. Now we can just work through. You can kind of tell if you're on the right track, because once you get to this point, it should look like it's going in the right direction. Otherwise, you could end up with something that doesn't look quite right. So just taking our du dx, so differentiating with respect to x, the derivative of ln x, you hopefully remember from calculus 1, is 1 over x. Basically, the derivative of this function, x, which is 1, divided by the function itself. And then we get the integral of this guy here, which will be the integral of this guy. So our v comes out to be increasing the power by 1, dividing by the new power. That's going to be x to the power of 3 over 3. Okay, so we can just go ahead now and plug these into our formula. So our integral is going to equal uv. So this is our u, this is our v. A little bit, well, not ugly, but I mean, it's not pretty, is it? It's x cubed over 3 multiplied to ln x. You could write it like that, or you could put the ln x on the top of that fraction as well. Either way would be fine. I'm going to write it like that, minus the integral of v du. So this is our v, this is our du. So putting those guys together, let me just actually write those. So I'll write it exactly as it should be. So v, which is x cubed over 3, times the du, which is times 1 over x, and we want to integrate all of that dx. Okay, now this guy's done, right? There's nothing more to do with that term, so just going to leave that one alone. I might actually just pull that ln x on top to make it like that. I think that's maybe a slightly neater way to write it. This guy here needs a little bit of work. So notice that here we've got a 1/3. If you've ever got a constant like that, you can pull it in front of the integral. So I'm just going to maybe pull that in front to make it 1/3 times the integral, and then we're going to have x cubed over x, because if we multiply those two fractions together, we're going to have, well, let me just do it over here to show that. So we're going to have x cubed being multiplied by 1 over x. So just using indices rules, this is going to give us x squared. So we can basically plug this in here. So tidying this up, we're going to get, well, this guy stays the same. So we get x cubed over 3 times ln x minus, I'm going to pull the 1/3 in front. So it's 1/3 the integral of this guy here, which we now know is x squared. So this becomes x squared dx. So still not quite done. We still need to evaluate this integral. I'm running out of board space here, so I'm going to pull this over here and just make some space. So pulling this guy up here. The first term stays the same, so we get x cubed over 3 times ln x. X squared, integrated, we increase the power by 1, divided by the new power, just using the power rule, so it's going to be 1/3 times x to the power of 3 over 3. Remember to put your constant of integration on the end there. We can simplify these guys by combining them, so we get x cubed over 3 times ln x. Multiplying these together, we get minus x cubed over 9 plus c. So this would be our final answer here for this product, this integral, using integration by parts. Now, just going back to the original assignment of the u and the dv, how did I know to make them that way around? Well, it's just based on experience really, because I knew that if I differentiated ln x, I was going to get 1 over x, and having done a lot of these questions, I knew that later on that 1 over x would multiply to an x cubed term to give us an x squared. In other words, to give us something that we can actually integrate. Whereas if we'd made the assignment the other way around, we might have found that this part would be okay, but we might run into trouble down here. And what sometimes happens is you go in like an endless loop and you just cannot find something in this part to integrate. And that's kind of what's going to happen over here, although it's not going to go in an endless loop, but we're going to find that after the first iteration of integration by parts, regardless of the assignment for u and dv, we get something here in the integrand which we cannot integrate. But we can't integrate it because it's in the form of a product, so we have to use integration by parts a second time. And that's actually really common in these questions. So I would say be prepared to see this, having to use integration by parts twice. So let's just move on from this example and take a look at this guy. Hopefully got enough space on the board here for this one. So I'm going to go ahead and I'm just going to write a little bit smaller here to try and fit this all in. So I'm going to go ahead and make my u equal to x squared. I'm going to make my dv dx equal to e to the x. And I would actually encourage you, as you start these questions, not only for the ones you've got to do twice, but for all of these, try the assignment of the u and the dv both ways around. Some of them will work, some of them won't work, but running into trouble and getting to a point where you can't take it any further, that's actually how you're going to learn how to make the correct assignment. So yeah, try mixing these up a little. So our u equals x squared, so our du dx, using the power rule, will just be 2x. Our v is going to be the integral of e to the x, which is just e to the x. So we're going to plug these guys now into our formula. So this guy here we'd evaluate to be uv, so uv, that's going to be x squared, e to the x, minus the integral of v du. So v du, so that's going to be e to the x times du dx. From here, du dx, which is 2x dx. Now, just tidying this up a little by pulling the 2 in front, and I'm also going to reorder the terms, so I'm going to make it 2 times integral of x e to the x dx. Now that's fine, that's all worked okay so far, but the thing that we've now got to integrate is in itself in the form of a product. So like I kind of suggested was going to happen, it's not in a form that we can just integrate. In fact, we've got to use the integration by part method again. So what we're going to do, we're just going to park this result. We're going to need this result later on, but we're going to have to deal with this guy here separately. So just pulling this out on its own. So now we want to think about the integral of x e to the x dx. Okay, so going back to our starting point, making our assignments again. So I'm going to say let u equal just x, so that du dx equals just 1. And that's always kind of what we're looking for. We're looking ideally for a number. If we get a number in there, then we know we're not going to go in this endless loop. It's not always a number, but that's a good sign basically. And we're going to let our dv dx equal e to the x, which just means that v would equal the integral of e to the x, which is e to the x. So plugging these guys into our formula again, this is going to equal uv, so u times v, that's x e to the x, minus the integral of v du, so that's v, which is e to the x, times du, which is 1. E to the x times 1 is just e to the x, so that's e to the x dx. So that's everything now plugged into our formula. This time though, we've ended up with an integrand that we can actually integrate. The integral of e to the x is just e to the x. So this becomes x e to the x minus e to the x, and then we put our constant of integration on the end there. So remember, we still need to plug this back into here because this thing here was just to deal with this part. We still need everything else. So the original evaluation, going back to this point, is going to give us x squared e to the x minus 2 times the integral of this, but the result for that is here. So that's going to be 2 times x e to the x minus e to the x. Wow, there's a lot of e to the x's in this question. And then we can just put our plus c in the end. You don't really need to worry about multiplying the plus c by 2 because remember the plus c, the constant is arbitrary. It can be any number basically. So we can just leave it like that. Multiplying out the bracket, we would get x squared e to the x minus 2x e to the x, and then a double negative there to give us a plus 2 e to the x, and then a plus c still on the end. There's a common factor here now of e to the x. You could pull out that common factor. Let me just show you that actually. Sometimes that will happen in these questions. So you get e to the x squared minus 2x plus 2. So basically getting a trinomial inside the bracket, and then still got the plus c on the end. So a little bit annoying, frustrating when you've got to do this twice, but it is really common, like I said earlier, so definitely be prepared to evaluate some like this. So not an easy technique, integration by parts, but it is a very common question type. It's a common scenario to have to integrate a product of functions. In the next class, we're going to take this a little further, and we're going to evaluate not only a product of functions, but a product of functions when it's a definite integral. We've got the limits here and here. So once you've got this technique down and you're happy with how this works, you've got a bit of experience, then we can move on to the next class and have a look at those definite integrals.